Greetings and welcome. In this session, we will discuss about the HVAC cooling load calculation procedure. In a previous video session of HVAC, we have seen a fundamental theory of HVAC, that is a psychrometry, that is a science of study of moist air where different properties of moist air are studied. After that, in air conditioning system, different processes which are used, these are called as psychrometric processes, that also we have studied. Then how to use different properties and how to get these values from the chart, that is a psychrometric chart. So use of this whole knowledge we are going to use in a today's video session for the calculation of HVAC cooling load. Now here are two cases. First one is a mixing before coil and another one is a mixing after cooling coil. In this video session, our objective will be for the mixing before cooling coil. So let us see the objectives. First of all, we are going to find different types of loads, especially here RTH means room total heat. That is a summation of room sensible heat and room latent heat. And grand total heat. Grand total heat is a load including from the outside, that is outside air sensible heat and outside latent heat. Then there are three types of factors which are located on the sensible heat factor scale. So these are RSHF means room sensible heat factor, GSHF means grand sensible heat factor, ERSHF means effective room sensible heat factor. After that, we get the condition of air leaving the coil. Then we find the quantities of total air which is passing over the cooling coil, that is called as dehumidified air. This quantity is divided into two parts, fresh air quantity and recirculated air quantity. And finally, we find the cooling capacity of cooling coil. Now this type of cooling load procedure is associated with air conditioning systems which are used in big buildings where the number of people are coming as an occupant. So maybe cinema theater, auditorium, conference hall. So here we can see the block diagram. Now this block diagram is of the unit that is a part of central air conditioning system, that is called as AHU, means air handling unit. In air handling unit, it consists of supply duct line, return duct line. This is a wall location. This is a mixing chamber and this is a cooling coil. So here via the supply, via the duct, outside air is taken, that is called as fresh air. This fresh air is mixed with the recirculated air, which is also called as return air, which is coming via return duct. These both air are mixed in a mixing chamber. After that, this mixed air is passing over the cooling coil where the air is processed. So in this, temperature and relative humidity of the air is controlled, and this processed air is then passing to the air conditioned space. Now in this case, to find the parameters what we have discussed in objective, we need data. So that data is given in the numerical. Here we need outside air condition and indoor air condition, that is a outdoor and indoor condition, in the form of dry bulb temperature and RH. Sometimes it may be given in the form of dry bulb temperature and wet bulb temperature also. After that, we should know the cooling coil surface temperature. It is called as DPT. It is also called as here ADP, means apparatus dew point. Then here the mixing chamber, here the both air are mixing. So percentage of fresh air and return air that is given. And to find the load at the room, that is a room total heat, and the load which is coming on the cooling coil, that is a grand total heat. So for that we are given in the numerical RSH and RLH value in a kilowatt. Now here if you see, this is a point number O, that is outdoor air, this is the condition, and here this is a point I, that is a indoor condition. These are the condition of air before the cooling coil 1, and this is after cooling coil 2. This is processed air, we call it as dehumidified air. That is why the notation we use here m dot d, dehumidified air. Fresh air we use notation m dot o because it comes from the outside. Recirculated air or return air we use the notation as m dot r. Now in the next slide we will see the location of mixing point, also location of this outdoor and indoor points. So by using the given data here, the condition of fresh air which is coming from the outside, dBT and RH, by using that value we locate point number O, point O. Similarly we locate indoor condition with point I, then we join this line O to I. Then we have to measure this length OI in mm. Then to find the location of mixing point, that is a point number 1, we use the concept. Here we are given suppose fresh air. So here whatever percentage of fresh air is given, this percentage which is at point O, this we show on the opposite side of the line OI, because it is based on the concept of mixing of air. So where the outside air is in proportion with opposite side difference, and this return air percentage is in proportion with this opposite side difference. So with this concept we can find the length I1 is equal to percentage of fresh air given multiplied by this OI length in mm we measure. Then whatever I1 length we get in mm, we locate point number 1 from I at that distance. Thus we get the point 1. Now this point 1 is air condition passing to the coil. It is a condition of air entering to the cooling coil. So from the psychrometric chart, that condition we can get as a dry bulb temperature, its relative humidity and enthalpy. After that, in the given data, ADP means apparatus dew point, that is a coil surface temperature. That point we locate on the psychrometric chart, this saturation curve. This ADP when we located, after that we join this 1 to ADP line. Then we have to calculate room sensible heat factor. For that we use this formula. Room sensible factor is a ratio of room sensible heat to room total heat. Room total heat is a summation of room sensible heat and room latent heat. When we get RSHF, then we locate that RSHF value on the scale which is provided here on the psychrometric chart. This is a scale called as sensible heat factor scale. So here this sensible heat factor is ranging from 0.35 to in a downward direction up to 1. So whatever value of RSHF we get, that we locate on this scale and we say that point as a point B. After that we locate point A, which is called as alignment circle, which is suggested by the ASHRAE, that is American Society for Heating, Ventilation, Refrigeration, Air Conditioning Engineers. This alignment circle is a reference point which is a combination of 26 degree Celsius DBT, that is a dry bulb temperature, and 50% relative humidity. Then we join A, B. This line AB, we can see here, this RSHF line. Now this line is helpful us in further steps of the problem. So as we discuss here, we draw now a line parallel to this AB line through point I, that is an indoor condition, up to this saturation curve. This line is called as room sensible heat factor line. Then already we have drawn a line 1 to ADP, this red color line, and this I, or we say this RSHF line, blue color line. So we get here intersection of these both line, that is a point number 2. And this point number 2 is a condition of air leaving the cooling coil. So from the psychrometric chart, we can get the condition of that air that is leaving the cooling coil, means dry bulb temperature TD2, or relative humidity phi2, and enthalpy H2, which is these values are useful us in the next procedure. Now the air which is coming from the cooling coil, that is a point number 2 condition, that air is a passing. Now this is a dehumidified air and cooled air which is passing to this hall. So here will be what? Enthalpy of this air, that is H2, after the cooling coil. With this enthalpy, this cooled air and dehumidified air, cooled and dehumidified air, when passes to the room, then in the room what the load present, that is RSH and RLH, that load is added to this air, and thus when this air is coming out as a return air or recirculated air, here we find this enthalpy, that is HI enthalpy, because it is coming from the hall outside. So thus the amount of load in the room total, that is RTH. So RTH, how to find? So RTH will be what? Dehumidified quantity, means this total air, multiplied by this enthalpy difference, that is HI minus H2. So here these values, enthalpy values, we get from the chart. Here this is an enthalpy scale. When we project a line from I and point 2 on the scale, we find here HI enthalpy and H2 enthalpy in kilojoule per kg. These enthalpies we put or use in this formula. Thus RTH means room total heat, that is in the form of RSH and RLH, that is a given data, so we put here. So from this unknown is what? M dot D, means dehumidified air quantity, which is in kilogram per second. So by this procedure or step, we find the dehumidified air quantity. Once we get total air quantity which is passing over the cooling coil, then we can find division of this total air into two. That already we have discussed. That is what? First is a fresh air quantity, that is passing from the outside air. Fresh air. So this quantity from the outside, thus the notation m dot o. How to calculate that? We multiply this dehumidified air quantity with the fresh air percentage given in the numerical. Similarly, we calculate this return air or recirculated air, that is m dot r. That is equal to what? Multiply this dehumidified air quantity with return air percentage given in the numerical. So we find fresh air quantity m dot o and recirculated air quantity m dot r in kilogram per second. Now we will see about the grand sensible heat factor calculation. Grand sensible heat factor is equal to RSH plus OASH divided by RSH plus OSH and RLH plus OLH. Now in this case, room sensible heat factor in that and grand sensible heat factor, here what is the additional quantities? OASH and OALH. These are outside air sensible heat and outside air latent heat, which are coming from the air, that is coming from the outside, fresh air. So here to calculate OASH and OALH, we use the formula m dot o means quantity of fresh air, outside air in kg per second, multiplied by this enthalpy difference. Now this enthalpy difference, how to find? So already we have located point O and I, outdoor condition, indoor condition, that we take here. Then we draw a horizontal line through point I, draw a vertical line through point O. We get here intersection point A. Then all these 3 points we project on the enthalpy scale. Suppose this is an enthalpy scale. So thus on the enthalpy scale, we find the values HO, enthalpy of outside air, enthalpy of room air, and enthalpy of this point HE. These enthalpies we use to calculate OASH and OALH. So OASH will be what? This horizontal enthalpy difference will be what? Sensible heat, HA minus HI. And this vertical line enthalpy difference is latent heat. So that we use here in calculation of OALH is equal to m dot O into HO minus HE. HO minus HE. Once we calculated these two, then addition of respective, that is RSH plus OASH, both are sensible heat. Together we get that we call as a grand sensible heat. Similarly, so room latent heat and outside air latent heat together is called as grand latent heat. Summation of these both loads, grand sensible heat and grand latent heat together, that is called as grand total heat in a kilowatt. Then by putting all these loads, that is OASH and OALH, RSH and RLH we are given in the numerical. So putting all those values, we get calculated GSHF value, that is grand sensible heat factor value. Now this value we put or locate on the psychrometric chart in the same way as we located room sensible heat factor. So here we use point number C to show GSHF, grand sensible heat factor, on the scale. Now already we have A, that is alignment circle point. We join this A to C. Now this is a line, we get a reference line. Now already we have drawn line 1 to ADP. Now this red color line and this grand sensible heat factor AC line, that these two lines should be parallel to each other. Then we can say the procedure what we have followed, that is correct. Thus this 1 to ADP line, red color line, this is called as grand sensible heat factor line on the chart. Next type of factor is effective room sensible heat factor. The formula is RSH plus OASH into bypass factor divided by same bracket, and then RLH plus OALH into bypass factor. Means in this formula, grand sensible heat factor formulae contained are as it is. The additional is what? Sensible heat and latent heat. These both loads are multiplied with bypass factor. This bypass factor is of cooling coil. So here we have got in a previous procedure point number 2, that is a air living cooling coil condition. So that condition means temperature of variable temperature of point 2 that we use here. Also we know the condition of air entering to the cooling coil, that is a mixing point. So that is a temperature TD1. So here the concept of bypass factor is what? The direction of the process is from 1 to towards ADP. So opposite difference divided by total difference. So opposite difference is what? TD2 minus ADP divided by total difference is what? TD1 minus ADP. So by doing the calculation we get the bypass factor. This bypass factor value we use in the calculation of ERSHF. When we get this value, again we follow the same process as of GSHF and RSHF. Here the point D we locate with value of ERSHF. Then we join line AD. Also we join this I to ADP line. Now this I to ADP line should be parallel to this AD line. So thus we call this I to ADP line as a effective room sensible heat factor line. So finally is a capacity of cooling coil. This is a cooling coil. Across the cooling coil we find point number 1, that is a entering air condition, and point number 2, that is a leaving condition. So we use the formula for the capacity, that is total air passing over this cooling coil, that is dehumidified air, m dot d, multiplied by enthalpy difference between point number 1 and 2. So these two enthalpies we find on the psychrometric chart. This is an enthalpy scale. So when we project point number 2 and point number 1 on the enthalpy scale, we find the values of H1 and H2. These values we put here in the formula. Thus we get capacity in a kilowatt. After that, if we divide this value by 3.517, then we get the value of a capacity in TR, that is turn of refrigeration. This is what capacity of cooling coil. So by following the cooling load calculation procedure for the case, that is mixing before cooling coil, we find the output in this form. that we have summarized here. Location of outdoor indoor conditions, that is point O and I on the psychrometric chart. Then we get the mixing point, point number 1. Then we calculate the loads, room total heat and grand total heat, and then factors, that is RSHF, ZSHF and ERSHF. After that we get the condition of cooling coil air leaving condition, that is a point number 2. Along with we find the value of dehumidified air quantity, that is a total air passing over the cooling coil to the hall. And subsequently we find the distribution of this dehumidified air into 2 parts, that is a fresh air and recirculated air quantity. And finally we find the capacity of cooling coil in a TR. So let us meet in the next video session of HVAC. Thank you.